Um, Good afternoon, everyone. For those for which this is afternoon, thank you for joining me. My name is Qasim. So today I'll be talking about Morse homology. Um, so I have a mantra for this talk. And it's that Morse homology is a way of counting holes in spaces by counting solutions to differential equations. Counting holes. This is related to the title in the sense that this is given the name of homology, more or less. And there are many ways of doing this. Morse homology is just one of them. So the differential equation that I'm referring to here, these will come from a so-called Morse function. That's the Morse part of the talk. Now, of course, I don't expect this to make sense to you. The whole point of the talk is to get to that point. Before that, before we start with math, I want to talk about something that not many people do, but I think they should. And that's why you should attend talks or how you should attend talks. Because if you listen to the why, then you'll understand sort of how you should too. And I was told that majority of my audience, they'll be third or fourth year undergrads in math. So I'm really tailoring it to them. So why attend talks? Well, one thing is that it increases your exposure. So you might have heard that math is really broad, but I feel like at least at the undergrad level, you don't really understand this. At least I certainly didn't. And it's really important to have this exposure to know what is out there. So for instance, with this talk, this topic, Morse homology, it broadly comes under topology and geometry. So you'll get to know a little bit about what this area of math is. And by topology, I don't exactly mean point set topology, which is something, which is the name for the thing that people are usually taught in their undergraduate. And likewise, geometry doesn't just mean Euclidean geometry. And more specifically, this topic, Morse homology, comes under the field of symplectic topology. So now you'll know a little bit about that. And second, it can be a chance for you guys to drop for thesis topics. So for those of you who are interested in pure math, and right now you are like really nearly finishing their studies, talks can be a good way to just learn about different topics you can do your thesis on. So I think Morse homology is certainly one of those. There are a lot of things, and I will make sure to tell you about as many things that you could do in this regard. And finally, I think the third thing is that it sort of complements your learning in the classroom. So right now you're learning some of your core courses, analysis, group theory, maybe linear algebra. And you should think of these talks as a way to bridge the gap between like the core courses and the more advanced topics in math. So maybe this will give you more motivation to study those core topics because now you'll know that they actually come up somewhere down the line. And again, to connect it to my topic, in this talk, you'll see the second derivative test come up, like from calculus, and also differential equations. And don't worry, you won't actually be forced to solve any. Um, you'll also see quotients, maybe from algebra. and a little bit some definitions from topology come up too. But I'll try to make it as self-contained as possible. But another point to make sure to that I want to emphasize that this is not really a substitute for a lecture, nor is it meant to be. Like with my talk, I will not go into many of the proofs or details that I think are distracting. And if you keep these points in mind, ultimately doing this will help you nudge yourself in the right direction. So, I mean, find the part of math that you might find interesting. So, for instance, with this topic, this is really more for those who are maybe interested in analysis, calculus, and also topology. There's a little bit of algebra too, but it's mostly for people who like analysis and topology. And there are certainly algebraic parts when you in the field that I think it takes quite a long time to get to that. And on a final note, it's important not to be discouraged if you don't get a lot of it, because I was really in the same place as most of you. So, and that's because these ideas are highly non-trivial. For instance, with this talk, I mean, I think it took nearly half a century um, to develop this whole theory. And I hope you will keep these things in mind uh, for the rest of the talk. Okay, enough about this. Now back to math. So the outline for this talk is going to be as follows. We'll have um, 5 parts. Uh, yeah. Okay. So um, the first part will be about homology. So I'll just give a basic introduction here. And the goal will be to remember the mantra, the counting holes part. We'll try to make sense of what holes are and how do you count them. Second part will be a primer on Morse functions. So you can think of these functions as those functions for which the second derivative test makes sense. And the second part will be about counting gradient flow lines. So essentially, we'll take gradient flow lines between critical points of the function that I'm talking about in the third part, in the second part. And the fourth part will be about finally defining what Morse homology is and a few examples. I'll also give a little exercises for those of you who are interested. And I'll end with some outlook on some interesting results from this. Now, what should you expect to take away from this talk? You'll see a little bit of taste of what algebraic topology is. So this is the part of math where you assign algebraic things to topological spaces. In a way, this invariant under deformations. You'll also get to know a little bit of dynamics, maybe. And by the end, you can you might be able to compute homologies of a few spaces. And also maybe a minor point, but those of you who are more interested in like applied things, discrete Morse theory has some applications in topological data analysis, and this is still one thing that people are still looking into. So maybe that's interesting for a few people. Okay, so let's formally start with the first part of the talk, homology. Now, a general theme in mathematics is classifying things. For that, you have to come up with a good definition for what means for two things to be similar. And the way one classifies topological spaces is by saying that two things are similar if you can deform one into the other without tearing anything apart. Okay, and so for instance, with this diagram that I'm drawing, now you can sort of imagine that this round sphere that I've drawn is yeah is the same as this one, as this bean-shaped sphere. So maybe you'd want to put them in the same category, but you wouldn't want to put these two in the same category as this second thing. And maybe your instinct would be that, well, there's a hole in this thing and there aren't holes in the other thing. And that would be right. That's precisely what it is. But it's the idea of holes is actually not as clear as one might think. Or at least it's not entirely straightforward how one actually formalizes what we mean by a hole. I mean, it's not exactly the central cavity. So this thing, it's not this for a mathematician, because it's really something that's outside of the space. And mathematicians, they like to define things intrinsically, which is just a fancy way of saying that we want to make a definition that depends really on the points of the space. Okay, so maybe well, one way that is formalized is that holes are supposed to be loops that don't arise as boundaries. Now, what does that mean? So, for instance, with the torus here, if you think about this, if you take this meridian circle on the torus, then this is a loop, right? Maybe I should really say 1D loop, right? Because implicitly that's what I'm assuming here. So it's a one-dimensional thing, but it's not a boundary of something, at least not in the space, because when I'm trying this, I'm assuming this part, the inner part, is not really in the space. If you notice that this is exactly something that's not something in the torus, but not in any of these things. Because if you take any loop, right, if you take any loop here, it arises as a boundary of this 2D region, right? The cap on the top. So there's the sphere has no loops. Holes, sorry. But the torus, it has holes. Great. So that takes care of what a hole is supposed to be, at least intuitively. Now, how do you count them? And we want the count to be finite too. Otherwise, we wouldn't be able to distinguish things if there are infinitely many holes. So you might want to, right now, the way I've defined what a hole is, then at that logic, this is a hole. So is this. Right? All of these are holes. But maybe we want to say that all of these ones are the same type of holes. But so, for instance, this one, the longitudinal thing, this is also a loop, which does not arise as a boundary of something, the space. And maybe we want to say that this is fundamentally different from these types of loops. And the final answer maybe is that there are only two holes on the torus. So the way you do that is you count holes, but up to something. That something is that we consider two holes to be same. So hole one is equal to hole 2 if there's a region whose boundary is equal to hole 1 plus hole 2. And if you count only up to these things, then notice that with these two meridian holes, you have a region. It's this one, right? And and its boundary is exactly these two things. And also, I want to ask: is my cursor visible when I do this? Anyone?
Yes, it is. Yeah.
Okay. Thank you. Yes. So, okay. So now, if you count, so this is our definition of what a hole is, an informal definition, and this is our definition of what it means to count things. So if you do this, then on the torus, there's really two holes. Okay. Now that's one thing. Another clever insight that mathematicians had is that there's actually no reason to talk about a one-dimensional hole. Notice that the whole notion that we've defined, it's a bit more general than how it seems. The only thing we would maybe need to generalize is what it means for something to be a loop in higher dimensions. But otherwise, everything in this makes sense, even in high dimensions. So the insight is that it makes sense to talk about a key dimensional hole. In some sense, that I haven't made precise, but at least intuitively it should make some sense. Mathematicians have a fancy name for these things. They're called the Betty numbers. Okay, and maybe let's denote them by BK. So this is really what we mean by a k-dimensional hole. So these count k-dimensional holes. That's maybe B1 is this, B2 is this. Just to like make it perfectly clear, let's compare both the sphere and the torus. Right? So there's 0 one-dimensional hole, right? We agreed on that. Any loop here always arises as a boundary, so there are no holes. And on torus, there are many holes, but if you count the right way, there are exactly 2 of them. Okay, now B2. Well, here's the tricky thing. So if you think about what a two-dimensional loop should be, then it should be somehow periodic in every direction, right? And if you take the surface of the sphere, then that's one candidate, right? It's a loop, and it doesn't and it doesn't come up as a boundary of something, because for it to be a boundary, there would have to be some three-dimensional thing in the space, but there is not. So this part of the definition is not really required for B2 case anymore. But the thing that's restrictive is what a two-dimensional loop is. And the only thing that can be a two-dimensional loop is sort of the surface of the thing that we're talking about. It can't be anything small, because if you imagine taking a strip, maybe, then certainly it would be periodic in one direction, but not in the other one. So that means that both, like for the sphere and the torus, there's exactly one two-dimensional hole. And it's the surface. And it corresponds to the thing that's inside the torus or inside the sphere. So the two-dimensional holes, they correspond to these things. But now, if you're a little clever, you can also think about what a zero-dimensional hole should be. Because according to our definition, it's just a zero-dimensional loop that is not a boundary of something. Okay? And a point is a loop because it has no boundary and does not arise as a boundary of something. So every point is a zero-dimensional hole. But remember that we count up to this notion. So you don't just say that, okay, this is a zero-dimensional hole, this is a zero-dimensional hole, this is a zero-dimensional hole, all of these are zero-dimensional holes. But all of them are the same, because what does it mean for them to be the same if you can find some one-dimensional thing whose boundary is precisely this thing? And there is. It's this line segment that's joining them. Right? It's not really straight, but it's supposed to be a perspective drawing. And for now, it should make sense to you that this is counting is the number of connected components. So if the space is connected, meaning there is a path from any point to the other, there's exactly one zero-dimensional hole, both on the sphere and the torus. But if you consider two spheres, right, disjoint from one another, then you would have two zero-dimensional holes. And that's another reason that these, if you, for instance, look at maybe papers of Morse from 1925, then you'll notice that he actually doesn't call them Betty numbers. At that point, he calls them connectivity numbers. And now maybe it should make sense, but also another perspective that maybe elaborates a little bit more on what these holes are supposed to be is that, and this is a bit of a sideline, it's not really necessary for the remaining thing, but BK, another way to think of them is that they're essentially the maximum number of key-dimensional curves that you can remove from your space before disconnecting it. So that you can remove before disconnecting it. And maybe that makes sense now, because if you look at this case of this sphere, if you take any loop on the sphere, you take it out, the space becomes disconnected. So B1 is 0. For the torus, even if you take out the meridian and the longitude, there's still a way to go from one point of the space to another. So the maximum number is exactly 2. Okay, so far we've looked at two different perspectives on what the Betty numbers are. Great. Now, getting back to homology. So technically, a little bit, because homology is not exactly numbers. I did say that it's a count of holes, and it does do that, yes. And even if it were numbers, I still have to tell you some explicit way of getting them instead of like looking at a space and eyeballing it. So there has to be some mathematical way of getting these things. And the way one formally gets these numbers is this general idea in algebraic topology, which is that you assign algebraic gadgets to spaces. So you assign some algebraic thing to space, right? And you do it in such a way that it's invariant under deformations of the space. So whatever algebraic thing you assign to this and to this, they should be the same. Okay, and ideally they should be different for this one. The point is that if they're different, then that means you can distinguish spaces just by using algebra. What I mean by algebraic gadgets are maybe, maybe you assign a group to a space, maybe you assign a vector space to a space. So anything that you've learned, maybe assign a ring. So anything that you've learned in your courses in algebra. And for our talk, what we'll be doing is we'll just be assigning vector spaces. So for this talk, we'll be assigning vector spaces to topological spaces. And in that case, the only information is the dimension, really, right? Because if you remember, so there's this theorem from linear algebra, which you can take as a fact that all finite dimensional vector spaces. And also remember that it makes sense to talk about vectors over any field. It doesn't have to be real, right? So over F, so any field is isomorphic to copies of anything. That means that a vector is just an n-tuple of entries in some field. And the reason I bring this up is because for this talk, I'll work exclusively with the field, the simplest field possible, which is just 0 and 1, and you do addition, mod 2, and you do multiplication, mod 2. Why I'm doing this is I'm not going to talk about it now, but you can certainly ask me later. And this might even be good. It's not really trivial. Okay, so yes, so what that means is that I'll be assigning C2 copies of C2 to a space. And the only information that you can get out of a vector space is really the dimension of the space. So maybe that gives you some hint for how this connects to what I said to what I said like here. These petty numbers will arise as the dimension of vector spaces that for which there's some formula or way of computing just from a space itself. Okay? So just a little bit of an example. So now this is actually what a homology is. Okay, I mean, and really I should say the kth homology, because now we know that it doesn't just make sense to talk about holes. It's better to even talk about different dimensions of holes, because it gives you even more ways to distinguish spaces, right? So, so for the sphere and the torus, this is what the homologies look like. Example of kth homologies. Okay, in C2. So we want a vector space over Z2 whose dimension is exactly 1, 1. So in both cases, it's just Z2, Z2. And we want a vector space for this, okay? For H1, we want a vector space whose dimension is 0. There is only one vector space whose dimension is 0. It's the trivial vector space, so 0. And we want a vector space whose dimension is 2. Remember our general formula, this is just C2 square. And with this, it was just 1, 1, so it's just C2, C2. Just to make sure that you're not lost, again, this is what I'm doing now is I'm telling you what the final answer will be when we actually compute these homologies. Okay? So I'm really like doing it in like a reverse order of sorts, just to give you an impression for what you want the final answer to be. So far, what I haven't done is told you how you actually get to this point. Okay, how do you actually get the vector spaces from a topological space? And that is really what homology is supposed to be. So I'll call this a recipe for defining homology. So far, everything we've been doing has been more or less informal. And now we try to make it more precise. So successive approximation to the truth, if you will. Okay, and the first step to defining a homology, so there are two steps to defining any homology thing. the first step is that given a space M, you assign something called a chain complex. And this is just a fancy name for a bunch of vector spaces, one for each integer. Okay, so there's one for ck minus 1, k, and so on for every, I think I said integer, but like every natural number. And so you have these vector spaces, c naught, ck minus 1, one for each k, and you have linear maps between them. If you don't like the term linear maps, think of matrices. So they are really matrices. So you have linear maps between them. And so for a chain complex, this is what it is. And the condition is, because so far I haven't really imposed any condition. I just said the chain complex is just vector space one for every number, and there are linear maps between them. But the final part is that you require that if you apply any two maps in this chain, you should get 0. So that means if you first apply partial k plus 1, and then you apply partial k, you should get 0 every k. Okay. Now I understand this was a little bit abstract. So let's just see a simple example of this. Okay. A simple example would be, so what do we need? We need to assign a vector space for every integer, natural number. Okay, so let's just assign the simplest one to a one-dimensional vector space. Okay, so we have a one-dimensional vector space, one-dimensional vector space, one-dimensional vector space C2. And we also need to define some linear maps such that they square to 0, right? But the easiest way to do that would be to take every map as 0 map. So this would take every vector to 0. So this would be an example of what this thing is. Okay, hopefully that's clear. This is what I mean by chain complex. I'll elaborate a little bit more. Just be patient. I'll give a bit more intuition. So now for the actual step where we define what a homology is. So the nth homology, or maybe just the kth homology, I guess, is something that you notice if you look at this this condition that I just came up with out of nowhere. If you think about this condition, notice that another way to phrase this is that if you try to look at the kernel of partial k, so this is the thing that I'm calling partial k, kernel means what are the things that it's taking to 0. Well, you don't know many things there are, but you certainly know that the things that come from the image of this map, they certainly get mapped to 0. Okay? And so the way we define HK is that it's supposed to be a comparison of these two things. So you look at these, that's the kernel thing. This, you can think of these as loops, and you mod out the image of partial k plus 1. And for those of you who have taken algebra, this is what you see as quotients. So if you've seen a little bit of group theory, then this is the quotient of two abelian groups. I said vector space, but really the only thing that you're using is the addition part of the vector space. So, okay, and now if you get got a little intimidating, like with the whole thing. I agree, this is complicated, but just try to bridge this with what I said earlier. I've just said the same thing, but I've translated it to more algebraic terms or more mathematical terms. The CK, they contain key-dimensional information. Okay? And this map, the partial key, these maps are supposed to be things that tell you what are the things in CK that are actually loops. Okay, so that's the kernel part. You're actually seeing what things are loops. And the other point of the map is that it tells you what a boundary is. So we don't want to just look at loops, we want to look them up, to count them up to a boundary. And that's what this is. So it's the same thing, but done more mathematically. So this is what a rigorous definition would be of what homology is. And the thing is that once you have a chain complex, okay, so once someone hands this thing to you, a bunch of vector spaces with linear maps that satisfy this property, then actually computing homology is very straightforward. You just need to do this algebraic thing. If you know a little bit algebra, you should be fine. The thing that distinguishes one homology theory, and I said that this is a general thing, from another, is what exactly is in this CK. So there are homology theories such as simplicial or singular homology, where these CKs are very geometrical objects. Okay, you can talk. You can ask me about this later. I won't talk about it now. But for us, these will be critical points. So these are points where the derivative vanishes of some nice functions, which I'm just going to talk about now. The hard part, I just want you to remember for setting up any homology theory, is actually showing this part. So showing that, I mean, you can come up with any linear map, but showing that all of them square to zero, that's a little bit non-trivial. And so what is the upshot of this section? The first section is that now you know the algorithm for computing homology. Okay? Maybe you got a little bit of motivation for it, but really you can just think of this as sort of just the way one computes homology. So I'll go for computing homology. That's what we've gone. And the reason I say this is because in the next section, we'll actually use this algorithm. And in terms, okay. But already, if you're with me so far, you've learned a very non-trivial idea in topology. So you should congratulate yourself for that. Okay, now next section. So like Morse functions. What are these? Remember from the very beginning of the talk, I mentioned that these are supposed to be functions for which the second derivative test works. Okay, and now I'm going to write the formal definition. So this is a smooth function from some space to R, okay, so a real valued function, such that critical point. So critical point is just a point where the derivative of the map vanishes. Critical points are non-degenerate. Okay, this is a fancy word. But what this means is the second derivative thing that I talked about. So maybe if you remember from calculus, there was something called a Hessian. Because, you know, I didn't say that this M is just R. It can be R squared, it can be R cubed, so any dimensional thing, right? In general, there's not just a single second derivative. There's lots of them, right? So for instance, in 2D, you'd have something like this. Right, so, and we say that a critical point, so where derivative vanishes, right, is non-degenerate. If the Hessian evaluated at that point, so it will just be a matrix, numbers, and non-degenerate just means that the determinant of this thing is non-zero. In other words, the matrix needs to be invertible. That's all a Morse function is. Now, why did I say that these are functions for which the second derivative test holds? Well, let's just recall what the second derivative test was from calculus, like, maybe from your FSC days. You remember that that in 1D, okay, so if M is just R, right, then you have this test which tells you what a critical point is. So if you have like a function, okay, and okay, maybe yeah. So if you have something like this, this is a point where the derivative is 0, right? The slope is horizontal, and here, notice that if you take the second derivative at this point, right, this is a minimum, right? So the second derivative, that's positive. It's concave upwards. I think that's the formal term for it. So, and the second derivative said that if the f prime plus f double prime was positive, f double prime was negative, then this is what a minima and this is what a maxima, right? But if it's 0, you can't say anything, right? That's the important part. You can't say anything, nothing, right? So that's why we have this condition that we want only those functions for which have critical points, but at all of those critical points, second derivative does not vanish. Okay, great. Now the thing is, that's one part. The second part is that in higher dimensions, critical points, which are non-degenerate, right? So which satisfy this condition that I've talked about, they are not just minima and maxima. You have more room in 2 dimensions. So if M is R squared, so that means there are more types of critical points that a function can behave in different ways. So I sort of copied this thing from so some so from Google. So this is a plot of different types of critical points. Notice that this is so 2D critical points. This is a graph of a 2D function because the graph is now in 3D. Now there's a third possibility. The reason that happens is because you have more room, so you have more directions. And the right thing to classify critical points ends up being this following thing. I'll just write this and then we'll see it in the sample. So what we do is that we count number of independent directions in which a function can decreases. Okay, so this, we'll call this a Morse index. So we'll assign a number to every critical point. What do I mean by this? And let's go back to the example. So notice that for this critical point, for a maxima, if you're at maxima, then, if you're at the very top, then in any direction you go, the function will decrease. That's what it means to be a local maxima. So there are exactly two independent directions in which the function decreases. But you can have maybe one direction in which the function decreases and another direction in which the function increases. That's what a saddle point is. So notice this. If I go like here, my function increases, but if I go down there, like on the other direction, then my function decreases. So this is it turns out that this is the only way in which critical points can differ from each other. I'll talk about why that is. But suffice to say that you can distinguish critical points in terms of directions of decrease. It can also could have also been directions of increase, but it's a choice, and we settle on this. And for a minima, how many directions of decrease are there? Well, there's zero, right? Because it's a minima, so in any direction you go, the function is supposed to increase. So the thing that formalizes it is it says that the only way to distinguish critical points is precisely by how many directions there are in which the function can decrease. And the way it says formally is that it's something called the Morse lemma. So you don't need to know what this is. If you go on this, it's just for those who are curious for how exactly this is made a bit rigorous. The thing is that for any so for a function and about any critical point, say p, the function locally looks like this. So a bunch of negative things. So plus a bunch of positive things. So you have to do some coordinate transformation, but after that, you can ensure that locally every f near p is this. Okay, this is what Morse lemma is. And Morse index is just supposed to be, you count the negative signs in this. Okay, so in this there are k negative signs because each one corresponds to decrease, right? These are quadratic things, so so the negative sign means that they will decrease. And remember, notice that this is, well, what is this? Each of these are precisely this, right? Like this is negative x1 squared plus x2 squared, and this is what? If you know how to plot this is exactly this, and what is this? This is exactly x1 squared plus x2 squared, right? So this should make sense a little bit now. So, okay, great. I guess one final thing about Morse functions is that to notice from the graphs of these, or maybe just from the expression that are given, that there are no critical points nearby, right? There's only a single point where the derivative vanishes. So if you remember a little bit of maybe some definition of topology, the formal way one does is that corollary critical points of Morse are isolated. If you don't remember the definition of what isolated is, it really is the English thing, more or less. So no need to worry about that, but this is is critical points, they don't cluster around each other. Okay, they're very far apart from each other. And remember that we've been talking about Morse functions, but I haven't given you a single example of what a Morse function is. Right? So maybe instead of an example, let's start with a non-example, okay? Because now we actually have a way doing this. So take the torus, okay? And keep it horizontally flat. And define the function as being just the height function. Okay, so what do I mean by the height function? It means it takes 3 points and just returns c. Think about the critical points of this. Critical points, they're not isolated because it's this circle, like just like you really, I mean, this is a terrible drawing. First, but you should be able to see that you have a whole circle of points where the height reaches its maximum. So at all of these points, it's the derivative vanishes. So this is not a Morse function. Okay, not a Morse function. But there's a very easy way to actually make it a Morse function. It's a little clever. To do is you just take this torus, okay? So this is a proper example. Well, of course, any of the examples you know from like calculus, those are perfectly fine. Maybe these are a little bit more geometric examples, take the torus and just make it stand out. And now, what do you notice? You take the same function, take, it's not the same function, of course, technically, because now you change the space. But if you do this, then what are the critical points? Okay, sure, this has got to be a critical point. It's a maximum. This has got to be a critical point. There's also others. It's this one and it's this one, because this is, you have one direction in which it decreases, right? And one direction in which it actually increases. Like if you go in this direction, it decreases, but in this direction, it increases. It's actually what we were talking about earlier. So the point of this section was that you have critical points and you can assign a number to them. So with this one, again, indexes, Morse index, that's the fancy name. It's 2, right? Because there are 2 directions in which you can decrease. Minima always at 0. And for both of these, you have a single direction for both of them. Okay, great. Final thing for this section is that theorem or fact, Morse functions are dense. In, well, C2, C infinity, something. So they kind of like rational numbers. They're, in fact, they're even better than rational numbers in some sense. But the point is that there are lots of them. Okay, so on any M, okay, so take any space at all, like any smooth manifold, whatever. There are lots of Morse functions. So in particular, what this means is that the set of Morse functions is not empty. Dense set certainly can, empty set can be dense, right? So this is really nice, because otherwise, if this was not true, then there would be no point in me talking about Morse homology. There's no point in talking about something that doesn't exist, after all. So, okay, these things exist. And, even if you have something that's not, you can like perturb it a little bit and you'll get a Morse function. This is what we saw in the example above. Now, so upshot, even if you like don't want to like listen to the rest of this, the upshot is that so far what you've learned is a huge thing. You've learned how nice functions, so Morse functions, look near critical points in high dimensions. So you already knew this in 1D, 2D maybe, but now you know exactly what they look like in every dimension. This is a huge deal. Okay, so now you know a lot more about calculus at this point. And for those of you following the rest of the talk, well, how does this connect? Well, remember you'll have to keep in mind this algorithm that we talked about for defining homology. This decay that come up here, they are related to this, the Morse index that we have defined. Okay? The way they relate is that the critical points of index k are precisely the thing that lead to CK. Okay? There's a easy, simple way of making them that which I'll talk about in the 4th section. But the thing that I have still not told you about is, where do the partial k come up? Right? How do they come up? I have yet to talk about that. So this is what I'll do now. So counting gradient flow line. This is the 3rd part of the talk. Maybe it seems a little fancy, but hopefully not scary. Okay, so and this is a very applied idea too, like gradient flow. Maybe if you've heard about machine learning and stuff. Anyway, it's not relevant. Okay, so a Morse function allows us to talk about gradient flow lines. What do I mean by that? So let's just have a very simple example in mind. So the simplest example would just be a sphere, okay? And again, take the height function. This is Morse. There are exactly two critical points, the top and the bottom, right? This is index 2 because it's a maxima. This is index 0 because it is a minima, and that's it. Okay. Um, the thing that you can do is the definition of, this is the definition, gradient flow line through P, a point in M. Okay. So one, you imagine, so start with point of the space, okay, the start of P. So you imagine that you are on the sphere and you're at this point, okay? You're at a point on the sphere. And what you do is you follow the direction of negative gradient. Okay, what do I mean by this? Again, you don't need to even know what gradient is, more or less, for this. The thing that we're doing is, so we have a function on the space, okay? And uh, you can take the gradient of this at every point. So by taking the derivative, this gives you a vector at every point of your space. Okay? And the only thing you need to know about a gradient is that it points in the direction in which the function increases the most. Okay? And here, since I'm talking about the negative gradient, that means this is always going to point in the direction of maximum decrease of the function. Okay, so you can imagine your whole space is like full of these vectors, and they're just there. So if you were actually imagine yourself on the space, you just have to follow these arrows, and you see where that takes you. That is what a gradient flow line. Okay, so just to like sort of have an intuitive picture in mind, if you do this here, what should you expect? Well, you want your function to decrease the most. So it certainly can't be this direction, right? Or this. There is a canonical one. It has to be this. The one that sort of gives the directly to the south pole. Okay. Maybe I went a little bit too fast. So, you follow these. The thing that you notice is that as soon as you like come near a critical point, your speed decreases because maybe I should be a little bit more precise here. When I say follow the direction, it doesn't just mean the direction. You should also would speed the magnitude of the gradient, right? So now here, where the critical point vanishes, you'll walk really slowly now. In fact, you'll actually never get there, right? Because you keep walking slowly and slowly and slowly. And only in infinite time do you actually get to the critical point, but you don't. So flow line, and likewise, if you did the whole thing in reverse, you follow the gradient enough, it will actually like negative infinity, you get to the other critical point. But the first thing to observe maybe is that and also maybe call them trajectory for short. Okay. So a trajectory through P is either equal to trajectory through Q, or they don't intersect. And that's the way I've described the whole thing. It's really it should be sort of obvious, because think about what would happen if this was not true, right? If you started with a point here, if you start from a point here and you follow the direction of the gradient, and somehow you cross this, then that would mean that the whole point was ill-defined and the whole algorithm was ill-defined in the first place. Because that would mean that here you were shown an arrow which pointed in this direction. Right? But there is a single arrow at every point, and it's the gradient. So that means that every trajectory they're all separate, okay? And maybe you can also see that they're, by the very definition, they cover the whole space. But the other observation that you notice when you were actually imagining yourself on the sphere and moving in this direction was that trajectories so in the limit really, so an infinite or negative infinite time, start and end, so at infinity, negative infinity at critical points. Because this is the only point where you could, right? Somewhere you have to, for you to stop, you'd have to have zero speed. So hopefully this makes sense. The upshot of the first thing is that when I see counting gradient flow lines, okay, now we are on the counting part, you consider a trajectory to this point and this point the same. Because sure, you start at a different point, but your trajectory is the same. The whole journey is the same. So you can think of this as, okay, maybe you can think of this as a motivational thing. It doesn't matter where you start. It's about the whole journey, okay? So, the whole journey counts. Journey counts, okay? So that's how we'll be counting things. And the trajectory and the limit starting and the critical points. This means that, well, in this example, we only had 2 critical points. But well, when you have more than 2 critical points, like the earlier examples, then maybe it's reasonable, since we're actually interested in counting these things, to talk about the spaces of, gradient flow line. So the way I've defined, joining A and B, where A and B are critical points of the function, the Morse function. Okay. Now, we might expect that these are nice spaces. So the space of all gradient flow lines from one critical point to the other, maybe these are good spaces, and they are actually, like for instance, with this example, if you take A and B betas, then example, what is M of AB? In one way, you can sort of think of this. So how would you count them? Remember, and this is sort of specific to why I'm taking the gradient, right? Because once it only intersects every level set, so every plane once. So one way to count them is to just like cut the whole thing with a single plane. And what do you get? You get a circle, right? And for every point of the circle, there's a unique gradient flow line. So that means that in this case, it's really one, so a circle. And in general, it turns out that this is well, okay, maybe I should give you a little bit more, one more example to convince you. So if you think of back to that to that bean-shaped sphere, what critical points are there? Again, the height function will be our Morse function every time. So here you have a critical point. This is a saddle point. You can sort of think of this as in one direction, there's a decrease, and in one direction, there's a increase. And this is a minima, right? Now, so you have 4 critical points of a function, height function. If you think about the number of flow lines, so between critical points, one thing you'll immediately notice is that there are actually more flow lines if the difference of index between them is larger. So think about this. think about these 2 points. How many trajectories are there joining this and this? Well, there is just one, right? And likewise here, one. But if you do this, but if you think about the trajectories that start and that like eventually get to here and eventually start from here and eventually get to here, tell most of them. All of these points, all of them. And if you intersect with the level set, it should sort of be clear that the following claim. That one thing is that these are MFAB, they're night spaces. So if you know what a manifold is, then these are those things under general conditions. And that there is a dimension to these things. And that's exactly the thing that we expect, more or less, that it's the difference between their indices minus 1. So the number of trajectories joining, say, this. So important example, if difference is 1, then dimension of M of AB is exactly 0. Okay? Right? Because if you intersect it with the level set, you can see that it only intersects at a single point. So, and if the difference is 2, and this is a theorem, I'm just stating it as like a fact, okay, but it's hopefully believable. And if the difference of indices, so these numbers that we've assigned to a critical point, is 2, then the dimension is 1. Just like the sphere case, right? And also here, you can sort of think of, if you intersect it, you kind of get an interval, right? Okay. Now, when I say counting, I really mean like enumerating, right? Like how many there are, 2, 3, 4 things. It's plausible that we can actually count the number of flow lines between 2 critical points, which are neighbors of each other. So whose index difference is precisely 1. Because it's a 0-dimensional thing, maybe it's actually finite. But there is a slight stability. Technically, if you, for instance, look at integers, they're also 0-dimensional. They're just full of points, but there are infinitely many of them. But the nice case would be is if they're actually finite points. And this is the nice case that we are hoping for. And we'll see that's actually true. Okay. So, that's like the third section. Now you will actually connect like section 1, 2, and 3 by getting back to the recipe that we had for computing homology. So maybe up. So we had step 1, we talk about the chain complex, and we talk about this homology. And we have to talk about partial K and somehow show that this goes to 0. So if you look at so this is section 4, defining Morse homology. So this is Morse homology. Already talked about homology. In first section, I mean. So we defined CK. CK, what was it supposed to be? It was supposed to be some vector space, but over C2. Okay, so its elements are vectors, but with entries in C2. The way one formally talks about them is you have the symbol EC2. Don't worry, I will explain what this says. So A are the index of A is equal to K. Maybe this is simple as a little scary if you haven't seen a lot of algebra, but this is what you're supposed to think of this. Imagine what is an element of this set, right? So anytime like you see some scary thing, you should really think of what are the things that are inside that scary thing. So in this case, the things that are inside this are really just formal combinations of critical points. So if you have a critical point A of index K and B of index K, so if there are exactly 2 critical points of index K, then this thing are all possible like combinations of A and B. So this could be like 1A plus 0b, or 0a plus 1b, 1a plus 1b, and 0a plus 0b. So this is really all it is. Okay? So the a and b, they're really just like placeholders. Think of when you're adding polynomials, you don't actually care about what x and y are, right? You just only add the coefficients. This is exactly the same thing. So this is what the ck are. And if you remember our fact, which was that this is that any vector space is isomorphic to some copies of V2. So in this case, they're exactly. So it's the number of so V2. So it's the number of copies of V2 that you're taking is just the number of critical points of index K. That's all it is. Great. Okay. We already established this. This is what I said would be the link between section 2 and section 1. The point of section 3, the gradient flow line thing, was to talk about a special chain complex. So talk about the partial K-map. This is called the Witten complex. Maybe also Morse Witten complex. There's also maybe like 2 other names if you want to be very, very fair to everyone involved. But I think the first one to do this was maybe Witten. Yes, this is the same Witten from string theory for those of you interested in physics. So the way one defines this is so if you have partial K plus 1 to ck plus 1, okay, how do we define this? Oh, this is supposed to be a linear map. This is important, okay? To remember that this is supposed to be a linear map, and that actually simplifies things a lot. Because what is a linear map? How do you actually define a linear map? Well, to define a linear map, it suffices to define only on the basis of the space. Maybe you remember this from linear algebra. If you don't, what it does is it's generalizing the concept that if you have a matrix and you want to know what the result is on after multiplying it by any random vector, all you need to know is what the result is of multiplying that matrix with some linearly independent vectors that form the basis of the space. If you know that, then you can figure out what happens for any other vector, because it's just going to be a linear combination of them. That's the idea. Okay, so yes, in this case, partial K plus 1. So what I need to do is define it on a basis of ck plus 1. They can, by definition, really, this was the point of the symbol, that we're looking at critical points really as a basis of the space. Okay, so when I say A, it's not really some abstract thing, it's really an element of this vector space. Okay, so for a critical points of index K plus 1, this is, well, it's supposed to be, now it lands in this space. This is also a vector space, so every element here is like a linear combination of the basis things. So so let's call them B, right? We'll sum over them. So these are critical points of index K. Okay, and well, it's a linear combination. That's the thing about linear maps, right? There are no powers or anything involved. So it's just going to be some number here. Okay, this is the part, these are the things which are valued in 0 or 1. And well, so here, this is going to be M of AB. So here is, so what I mean by the symbol is just the count of the number of flow lines from A to B. And this should be a little bit reasonable, because as I said, because this is 0-dimensional, maybe we hope that it's finite, right? So of course, technically I'm making an assumption. Assumption is that the M of AB for index A minus index of B equals to 1 is finite. Otherwise, this whole thing wouldn't make sense. Okay, that's assumption 1. I will justify why that is, but it really comes from justifying another assumption that I need to make. Because if you were attentive, this is not enough to define a chain complex. What you need to define a chain complex is the second part, is the fact that boundary squares to zero. And, if you want to remember, I have some geometrical way to remember this, think of sort of a triangle, a 2D triangle. If you take the boundary of this, you get a triangle, right? Just the boundary part. And then if you take the boundary again, you get nothing, right? You get empty. So this is really the symmetrical sort of observation here. Okay. So anyway, getting back to the point, that was just like a remark. So you want linear maps that one after the other go to zero. Let's see what that means. Yeah, I'll fill in that assumption. Let's apply partial key now. Let's apply partial key to this thing. Okay. So what do we get? Well, it's a linear map, and these are numbers. These are in C2. Okay, just numbers, 0 or 1. And it's a linear map. There's a summation. So I suffice to just apply to that and the B thing. So then, well, what do you get? You get that. So you get this index of. Well, then you'll land in the space ck minus 1, right? You'll land in the space ck minus 1. And so now you work with the basis of that, which is just the critical points of index k minus 1. So it's just going to be that. So C. And what is the thing that you attaches to? The number of flow lines from B to C, the thing that we call M of BC. Okay. And we already had this thing. So now this is what it should look like, right? Index of C is k minus 1. And index of B is k, right? Okay. So what it means for this to be 0 is that the coefficient of every C should be 0. But what is the coefficient of every C? The coefficient of every C is precisely M of A, B, fix C and A. The A is already fixed, but now fix also C. Then what we want is this thing to be 0. I also want to emphasize, what do I mean by 0? Because everything here was in C2. So it's really 0 mod 2. Okay? Now, what does this expression mean geometrically? Or combinatorially? This thing is counting the number of flow lines, the number of things. So if this was A, this was C, we fixed that. Okay. And, now let's think about all possible B's in here. This is counting the number of ways there are. So the first thing is counting the number of ways there are to go from A to B. The second thing is counting the number of ways there are to go from B to C. You're just taking the product of the B's. This just means all the possible ways you can go from A to C while taking a stop at B. So maybe we'd want to call them once broken trajectories. Okay. So now maybe it's a little bit believable that this expression, this is counting the once broken trajectories from A to C. Okay. I'm calling it broken because, it's not technically a trajectory, right? There cannot be any trajectory that goes from a critical point to another critical point and then to another, because at this point it will have to stop. Some sense, but okay. Right. So when I say that it's 0 mod 2, that means that the number of these things is even. Right? That's just a fancy way of saying that the number of things, if you count them, if you count all the ways you can go from A to B, if you multiply that all the ways you can go from B to C, take the product and take the sum, then it should be an even number. That's what we want to get. They come in pairs. So here, once broken trajectories come in pairs. That's the claim. So, right, maybe a little small, I won't call it a proof, but something close to a proof. Why should that happen? Step one, I will make some assumption. Suppose that these once broken trajectories, okay, they somehow they were, so suppose the number of once broken trajectories uh, arise as boundary of a compact one-dimensional manifold. Again, don't need to be scared of the word manifold, just means anything which is nice, like locally Euclidean, something. Then assumption holds. This is my claim. Okay. You don't need to understand why this is true. Okay, but suppose for a second that this was true. Somehow, all of these once broken trajectories, somehow they were the boundary of a compact one-dimensional manifold. Now, topology theorem, all compact one-dimensional manifolds are exactly of two kinds. It's the simplest thing that you can think of. A line segment. There's also another possibility. Can someone tell me what that is? Hello? Mm, Is there someone talking in the, maybe someone,
Sorry?
uh,
What
maybe
happened?
someone said in the chat?
No, those are
Okay. Yeah, no, I was just asking if someone would, like, someone had a guess for how many compact one-dimensional manifolds there were. So one is a line segment. There's one other example. Wait for a little bit in case anyone answers. It's the simplest. We've hint is that we've actually already talked about this. Okay. Yeah, I'll just tell what it is. So it's a circle. Okay. So um, so there are exactly two compact one-dimensional manifolds. They are a line segment and a circle. Okay. Now, if this is true, why does the step one hold? Because what are the number of boundary points? Boundary of a circle is equal to 0. There are no boundary points, but the boundary of a line segment is equal to, there are 2 points, right? Or well, even if you had like a bunch of line segments, the number of boundary points would be even. Okay, so then the assumption holds. So this concludes the proof if you were to believe this magical assumption that these once broken trajectories arise as the boundary of a compact one-dimensional manifold. And like again, if you don't know what that is, this is what that means: a line segment or a circle. Step two would be making it believable. Why the first assumption is true. And for that, maybe I'll just actually give you an example that we had earlier. Okay, remember that I keep drawing this bean-shaped sphere. There are two critical points. This. right? So, okay, so if this is A, this is B, this is C, then notice that what happens? Well, if you look at what are the once broken trajectories? First of all, how many are there exactly? Let's actually count them. Okay, how many trajectories are there from A to B? Well, there are single, one, and there there's also trajectory here. There's also trajectory here, the other side, from the other side, right? So there's one from A to B. There's exactly one from A to B, and there's two from B to C. So 1 times 2 is 2. So the number of once broken trajectories is exactly 2. Okay. So at least in this case, we see that. But how would this be somehow true? Why would once broken trajectories rise as a boundary of a compact of some one-dimensional manifold? Well, we do know what a one possible one-dimensional manifold is. If you remember, we computed the dimensions of these spaces, and the special case was when the difference was 2. In that case, the dimension was exactly 1, right? So the sort of thing is that if you look at the space of trajectories from a critical points with index difference 2, A and C here, then these spaces are generally not compact. So these are like, it can be compact. For instance, if you remember the example of the sphere in section 3, here, the space was really isomorphic to S1 for a circle. But in general, although they don't need to be compact, but their boundary can be like these two things. So that's really what I'm getting at here. And that should, geometrically, it should be reasonable. So step 2 was just make step 1 believable, right? And the way you can sort of see that is if you took a trajectory, right? If you took a trajectory from A to C, then maybe you can see that this is, if you just, if you keep perturbing it a little bit, right, then it essentially approaches either this trajectory or this trajectory. I'm drawing it terribly, but hopefully that makes sense. So the sort of there's a way to formalize this, okay? I'm just talking intuitively, but there's a way to make this geometrical statement formal. And if you believe that, that means that the space of trajectories from A to C, you can add these points to it, you can add these broken trajectories to it, and it becomes this line segment, or a bunch of these line segments, or a combination of these with a circle. So if I call this like compact version of this, then this is exactly once broken trajectory. Okay, hopefully that was a little bit believable. Okay, if you were a little lost, no need to be worried. Like, it's just okay. Again, the point is that coming back to maybe the definition for homology from the first section, we have a chain complex coming from the critical points, and these partial k plus 1, they satisfy the condition that they square to 0. Okay, that means we have a chain complex. I was just justifying why it's a chain complex. So now that means we can go to the fourth section. We can actually define what Morse homology is. So Morse homology, this is step 2 from section 1. So HK is equal to kernel partial k by image partial k plus 1. Okay, this is what it is for the Morse complex, for this exact complex. This is what it is. Right. Okay. Now, yes. Maybe one thing that I didn't talk about was the mantra itself, right? There was a little bit of a gap, maybe. that I said we'd be counting holes. We did that in section 1. We counted solutions to a differential equation. There's actually a section in we actually are counting solutions to a differential equation because my definition of what a gradient flow line was not precise, right? But if you were really noticing here, you should see that what is the formal definition? Formal definition would be that you are counting, well, not of this, maybe, okay. So a trajectory is just what? It's a map R to M, okay, such that the derivative, so I'm putting a dot here to mean a derivative, such that it's tangent, so this derivative vector is always the negative gradient, okay? So the velocity vector needs to be this thing. And this is what? There is a derivative here and there's an equation, so this is a differential equation. And what is this? This is just counting the number of solutions to this thing where x of negative infinity is A and x of infinity is B. Okay? This is the part where we are actually counting solutions to a differential equation. Of course. And if you don't like this, you can just say, okay, we are actually counting gradient flow lines or trajectories. Okay, but I want to emphasize this for another reason, but hopefully this makes sense now a little bit, what the mantra was and how is, but actually I haven't quite justified the holes part. Like, how do you count holes? Just from doing this. And this is where the theorem comes in. This is what makes the mantra precise, an exact theorem. HK is, they are independent of the Morse function f. Okay? This should really surprise you. Because I'm saying that to define this homology, okay, what did we need to define the homology? We needed the CKs and we needed the partial Ks. The CKs come from the critical points of the Morse function. If you take a different Morse function, you can have different critical points. Okay? And the partial Ks, they count the number of flow lines between critical points. If you change the function, of course, those are going to change. Now, the statement isn't that CK won't change or the partial Ks won't change. If I said that, that would be too surprising. So any math theorem should be surprising, maybe, but not too surprising. Otherwise, it's just false. So here, what I'm saying is that if you take the step 2, so if you do kernel and then mod out by the image, in every case, you're going to get the same thing. And this is really surprising because you have these vector spaces and you have these partial Ks, which you can really think of these as just matrices with numbers. And these numbers are what? These numbers are counting the number of trajectories from one critical point to the other. But so they're counting solutions to the differential equation that I described exactly in section 3, but with different boundary conditions, right? That's the information in a single, chain complex and these matrices that are in it. Okay? And somehow, just from these matrices, you can do a little bit of linear algebra and get exactly the number of holes. That is really surprising. Okay? And this is generally a theme in symplectic topology. So this field that I'm talking about, you can define many homology theories, but you use some extra data, but it turns out that extra thing is not actually relevant. Okay? So this is really what Morse homology is all about. And maybe just to wrap up, it would be good to actually give you an example of what Morse homology is, right? To actually compute these things. But if you've understood this so far, it's okay. Now now you may need a little bit of algebra to understand this. But remember that what we're doing here, if you remember step 1 and step 2 again. So yeah, from section 1, there's a special case of this chain complex thing, is if when all of these maps are 0, and all of these maps are 0, what happens in step 2? Right? I didn't explain this, but what happens in step 2? If all of the maps are 0, what does kernel mean? Kernel literally means, what are the things that it takes to 0? Well, things are the whole thing. So it would be C2, but you have to mod out by the image. But the image is what? The image, because it's a 0 map, it takes every vector to 0, so it's exactly 0. So that means the edge keys are exactly C2, okay? Because you're not actually modding by anything. In this special case, and it has nothing to do with C2, of course. The point is that if every map is 0, then edge key is exactly the C keys that you started with. This is a very special case, okay? Coming back to this, we can actually use this to define a very simple, to compute an actual homology of the sphere mathematically, okay? So the answer that I gave you in the very beginning of the talk, now you can actually compute it using this machinery that we have developed. So how do you do it? Well, in this case, you have critical points of index 2. So you have, let's call this A, let's call this B. Again, height function as usual. And C2 is exactly, C2 is exactly C2, right? It's exactly, maybe I should say AC2, 0, and BC2. Why? Because this is a maxima, so index is 2. This is a minima, so index is 0. But there is no saddle point. So there is none. That means these maps have to be 0. And so this means that the H2s, the H1s, the H0s are exactly the thing that we started with. So it's C2, okay? H1 is 0, and H1, 0 is C2. Okay, but now you might protest, okay, Qasim, so if you were never actually gonna mod out by anything or use quotients, then what was the point of like giving us the kernel and the image thing? Well, if you want to do that, then maybe you need to then maybe you can try out this example, the other example that we talked about, which was this bean-shaped sphere. So it has like 2 critical points here, 1 critical point here, and 1 here, and here. Well, what is this? What are the CKs for this? I call them A, B, C, D. Okay, so in this case, what are the CK? This is C2, the critical points of index 2. There are 2 of them, right? A and B. So it's AZ2 plus BZ2. C1 is CZ2, okay? And C2 is, C0 is DZ2, right? So this is just like, okay. So if this is this, and what are the maps? What are the maps between these things? Well, the map C2 to C1, this is not going to be 0. Uh, because how many trajectories are there from A to C? There are exactly 1. Likewise, exactly 1 from B to C. So partial A is C and partial B is C. Okay. And how many are there from C1 to C0? Well, this is understandable. C to D, there's 1. But you can also go the other way around. Again, this is a 3D drawing, right? So there are 2. So you get partial C is 0. Okay. And so that means that if you actually well, in this case, the kernel is clear. Okay, the kernel of partial 1, partial 2. So the kernel of partial 1 is exactly well, the kernel of partial 1 is just the whole thing. So it's C1. Okay. We still need to mod out by the image of the previous thing, but the image of the previous thing is well, it's what? It's exactly C1, right? It maps to the whole thing. So that means that H1 is exactly C1 mod C1, but that's exactly 0. Now, there are two things to be gained from this example. So this was example number 2. This was example number 1. We changed the Morse function. We had the same sphere, but in the end, H1 came out to be 0. So maybe this makes the theorem more believable, that it actually doesn't matter which Morse function you start with. Okay? And likewise, if you try to do this, what is kernel of partial A? Partial 2. That's exactly A plus C. A plus B. Because then 1 plus 1 is 2, which is 0. So kernel of partial 2 is this. And then what is H2? Kernel of partial 2 by image of the previous map, but the previous map is 0. So the image is 0. So that means that it's exactly just A plus B times 0, which is just C2. So we got the right H22. And we got the right H1. And likewise, H0 is just going to be C2. Okay? Great. Perfect. Okay. So now I'll just give some exercises if you want to try out a little bit more, just to test your understanding. So you can try to see what happens for this torus. Okay, and again, the height function. And if you want to make it even more challenging, you can you can add more holes. Again, use the same height function, find the critical point, look at their Morse index, count the gradient flow line, get this chain complex, apply step 2, and that's it. Okay. So yeah, that takes care of this final section. Maybe in a little bit of a outlook. Um, what one lesson from the whole thing is that somehow topology of a space is encoded in the critical point of a generic smooth function on the space. Okay, that's really the idea of the Morse part of the talk. That if you take a nice enough function, it can actually tell you about the topology. And there are like interesting applications that you can just immediately get just from the theorem. For instance, well, you see the HKs in some sense can maybe even be considered like as a subspace or something of CK. But the CK, or at least, you know, you can look at definitions. Because well, HK comes from first taking the kernel, so you get a subspace, and then you mod out by something, so that becomes even smaller. So an immediate consequence of this is that you remember the dimension of HKs were exactly the Berry numbers. So BK is less than critical points index K. What does this mean dynamically? It means that if you take a torus, okay, so it means that if you take a torus, and if you consider these functions for which the second derivative test works, then you are guaranteed that there are exactly at least four critical points. There, at least they have to be. So in any way, you can choose your function in any way, but you'll find that there will be at least four critical points. This is something that comes from the topology. So just notice how surprising it is. The derivative is something that's an analytical thing, right? It cares only about the local stuff. But the topology of the domain sort of forces this. So on a torus, any Morse function will have at least four critical points. Why? Because B2 was 1, B1 was 2, and B0 is 1. So there have to be at least four, right? This is something that you got just by knowing what the topology of the space was. And the reason I emphasize on the mantra so much, that you can count holes in spaces, that you can get homology by counting solutions to differential equation, is because this idea generalizes. And you replace differential equations with more complicated differential equations like partial differential equations. And that's something that you study in Floer homology. So you upgrade just the DE part to PDE part. And now maybe it's not very unbelievable that it should have something to do with the topology of the space. Okay, it is still a huge thing, and this is really a huge part in symplectic topology. And maybe another cool fact from Morse theory is that, okay, you have this question, what you can do is you can ask, if you have a Morse function on a space, and you know the number of critical points, what constraints does that impose on the topology of the space? What does that space have to be topologically? So if I tell you that I have a space M and a Morse function with exactly 2 critical points, so I'm saying exactly 2 critical points. You know one example of this, we talked about it, the sphere with the height function, there's 2 critical points. The Ray sphere theorem tells you that in any dimension, this is a consequence of Morse theory, tells you that the space has to be the sphere. So it's homeomorphic to the sphere. You can also ask the same question. So I have a space with a Morse function with exactly 3 critical points. What does the space have to be? In that case, the answer isn't exactly known. It is known in low dimensions, but I'm not really sure about how much is known. And yeah, one more thing maybe is that you can maybe the final thing that I want to make believable is just the part about somehow why it's independent, why the topology ends up being like, why the homology ends up being independent of that. And this is really comes from looking at Morse theory, which somehow tells you that you can decompose, if you have a Morse function on a space, you can actually split it into things. And those splittings come exactly at the points where they're critical points. So if you just take the torus and if you cut it, so you have these 4 critical points. If you take the torus and you cut it here, okay, and then you cut it here, and then you cut it here, and then you take the whole thing, turns out all of these pieces, they're topologically distinct. And if you cut at any point before a critical point comes, they're topologically the same. So in a sense, the Morse function, the whole topology of the space really is encoded in this. And this is something that you can learn about from Milner's book on Morse theory. So this is from 1960s. The topic that we looked at today, Morse homology, this is really coming from an idea of Witten, because step 1, step 2, they were all there. The step 3 part, the part where, well, we did people even studied gradient flow lines before this. I mean, in 1960s too. The huge insight was that you can use the count of these things to actually define a partial k plus 1 in the homology. So to connect the homology part with these gradient flow lines thing. And the fact somehow it's independent of f itself. So yeah, that I would, this is, I think, a good point to stop. Maybe I took a little bit more time. I'm sorry about that. But, well, yes, sorry.